All right? Okay, let's get it started then. Hopefully you can do that and pay attention at the same time. We are discussing L'Hopital's rule. This is what we started talking about last time. Last time we did kind of easy ones, I guess. I mean, today we're going to do some variations on the basic setup of the L'Hopital's rule. But the idea is, if we get 0 over 0 or infinity over infinity in a limit, we can take derivatives on the top and the bottom. This is the basic idea of the L'Hopital rule. So I'm going to write this as a, I don't think I ever actually wrote this out in a formal way last time, but this is a theorem. A theorem just means, like a true fact in math that you can prove. We're not going to talk about the proof, but I drew you a picture last time about why you should believe that this is true. But anyway, this is the theorem. It says if we have f and g, those are the function on the top and on the bottom. This is always about a fraction, right? A limit of a fraction. F and g are the numerator and the denominator. So if these are differentiable functions, they have to be differentiable because the whole point of L'Hopital's rule is you're going to take the derivative. So those functions, they need to be things which have a derivative. That's what differentiable means. So if f and g are differentiable functions and the limit as x approaches a of f of x is 0 and the limit as x approaches a of g of x is 0, that means when you try to plug the number in, on the top and on the bottom, you get 0 both times. Or, if this lim is infinity, and actually it can be plus or minus infinity, and the other lim is also infinity. So these are the two situations when you can use L'Hopital's rule. Sorry, G here. If, when you plug the number in, you either get 0 on the top and the bottom, or you get infinity on the top and the bottom, then, and here's sort of the rule that lim x goes to a, f of x over g of x is the same as lim x goes to a of f prime of x over g prime of x. This is the formula for the L'Hopital rule. It just says taking the limit of the fraction is the same as the limit of the fraction using the derivatives. All right, this is the L'Hopital's rule. So this is all about, it's about what we call indeterminate forms like 0 over 0 or infinity over infinity. If you ever encounter, if you're doing a limit and you encounter something like 0 over 0 or infinity over infinity, the proper response is to do L'Hopital's rule, all right? There are other scenarios, and that's what I want to talk about today. We may also see things like 0 times infinity. These are other kinds of playground conversations that you may have with your friends. What is 0 times infinity? Anybody ever thought about that before? It kind of feels like it ought to be 0 because 0 times anything is 0, but also it kind of feels like it ought to be infinity because infinity times anything should be infinity. The correct answer is 0 times infinity is an indeterminate form. It is like sometimes it represents 0, sometimes it represents infinity, or it might represent just like a number, a specific number. So this also is an indeterminate form, or also infinity minus infinity. This is another one where you might feel like, shouldn't that be 0? And maybe it should be 0, but maybe like infinity minus something else should always be infinite. Anyway, these are both also indeterminate forms. So if we see these, then you must simplify to force it, that says force. Simplify to force it into a fraction. And then do the L'Hopital rule. All right? The L'Hopital rule only works when you have fractions of things. So if you ever see these kind of multiplied indeterminate forms, 0 times infinity or something, you should write this instead as a fraction, and you may have to do weird things like stick something in a reciprocal rather than multiplication. You can write it as division by the reciprocal or something like that. All right? Simplify to force it into a fraction, and then do the L'Hopital rule. Okay? So I want to try a couple examples like this, and then we're going to go on to something else. I got 2, and then I got a few for you, and that'll do it for this topic. So let's try lim x goes to 0, x times natural log absolute value x. All right. So we should begin by trying to plug this value in and see what you get. All right. When I plug 0 in for x, if I just try to plug this in, it'll say 0 times ln of 0. Absolute value doesn't really make any difference. I'm plugging 0. The absolute value of 0 really is 0. So this says 0 times ln of 0. What is ln of 0? ln of 0 is not a thing like this. You know, you can't take the natural log of 0, but you should wonder, like, is it like infinity or negative infinity or something? And if you recall the graph of the natural log, this is the graph of ln x. It looks like this, right? So actually this, when I say ln of 0, that actually looks like negative infinity, because if you try to use a number close to 0 here, you're going to get an answer of way down here. So this actually looks like 0 times negative infinity. And that is an indeterminate form. You cannot just say the answer is 0. You may be tempted to say, isn't 0 times anything just 0? And the answer is like usually, but not if the other thing is infinite. Then you have an indeterminate form here. So this is indeterminate of the type, 0 times infinity. All right? So when you see that, you think, okay, I am going to do the L'Hopital rule, but L'Hopital's rule only applies when things are written as a fraction, like this. And this is what I said here. If you see something like 0 times infinity, you should simplify to force it into a fraction. All right? So I am going to do a weird simplification, which ordinarily you would never do it this way, but I have to make it look like a fraction. And I think there are a couple ways you could do that, but I'm going to write it like this. ln absolute value x divided by 1 over x. So I turned this multiplication by x, I turned it into dividing by 1 over x. All right? This is weird, and in an ordinary problem you would never want to do this, but they are the same. Multiplying x is the same as dividing by 1 over x. That's like the reciprocal of the reciprocal. All right? What's the point of that, though? Now when I plug this in, actually this, when we plug in, looks like infinity over infinity. Actually, it's negative infinity, but whatever. All right? Because of what we just said. When you do natural log of 0, that's infinite. And also when you do 1 over x, when x is becoming 0, that's also infinite. All right? The plus minus signs don't really matter. But anyway, this is a infinity over infinity type indeterminate form, which means we can do the L'Hopital rule. So we can do the L'Hopital rule. L'Hopital's rule. All right? And I hope you remember, the L'Hopital's rule is easy to do. I put a little h there to remind myself this is a weird step. I'm doing the L'Hopital's rule. You should do the derivative on the top and also do the derivative on the bottom. And it's still inside of a lim. Anybody want to say what's the derivative on top? Derivative of ln x? Surely somebody remembers. Yeah? 1 over x. Yeah, great. Excellent, Jana. I always feel weird saying people's names during class. I don't know, it seems somehow aggressive to me. I know people don't really feel that way, but I do know your names, at least many of you, but I may not say it. And on the bottom, the derivative of 1 over x. This you have to maybe think a little bit. Remember, 1 over x is the same as x to the minus 1 power, and so the derivative of that, I do the power, I bring the exponent down to the front, minus x to the minus 2, like that, all right? That's the derivative on the top and the derivative on the bottom. All right, and now I have to do this limit. Now this limit is still kind of weird looking, but before trying to do the limit, let's try and simplify. Actually, what we have here is just a bunch of x's in a fraction. So I think you should be able to like cross out something or something, right? This, if I were to write this in a more sensible way, it's weird to have 1 over x in the numerator. That's just the same as putting x on the bottom. And it's also weird to have a negative exponent in the bottom. That's the same as putting this up top. So this is actually the same as x squared on the top and x on the bottom, right? This 1 over x in the numerator is actually just like putting x in the denominator. And here, x to the minus 2 in the denominator is the same as putting x to the plus 2 in the numerator, all right? And this, now you cancel x's, and I get x squared canceling with x is just x, right? There's like 2 x's up here and 1 down here. I cancel them, I just get x. And there is a minus sign. So this is lim x goes to 0 minus x, all right? These are just simplifying steps. Basic, 7th grade algebra, although it is a little confusing to keep straight. The pluses, the negative exponents and all that can be confusing, but I'm not doing anything terribly fancy here. All right, and then what's the lim? This is now just 0, right? You plug in x equals 0 and you get 0, and that's the answer. So this is negative 0. It's not an indeterminate form anymore. 0 is just my answer. All right. It's a bunch of weird simplifying. Any questions about that one? Everybody done with the paper here? Yeah? All right. Everybody got it? All right. Thank you all. Nobody wants number 2. All right. Okay. All right. I got one more of these, and then I got some for you all. How about one more? This is a weird one also. Lim tan x minus secant x. Lim as x goes to pi over 2 with a little minus sign. That's not a typo. Lim as x goes to pi over 2 with a little minus. This is something that you will see occasionally in the homework problems. This little minus for these problems really doesn't matter. I mean, this minus, if it had been a plus instead, actually the answer to this problem is going to be the same. But the reason that it's necessary is because the tan and the secant, if you think about the graphs of these things, they have weird behavior around pi over 2. So I will just, this one, if you were doing this on the homework, you would probably want to draw a graph of tan, unless you just remember this. This is what the graph of tan looks like, and then it repeats the same shape like this, right? So when x is close to pi over 2, what is tan of x going to be? It's like way up here. And that's why this little minus would be written, if you saw this on the homework. This little minus refers to the fact that it should be up here, like slightly to the left, rather than slightly to the right, which would be way down here. So you're going to get different results here. But anyway, when I try to plug this in, it would look like tan x minus secant x is infinity for the tan x. That's because the value approaching pi over 2 from the left side, the value is way up here, all right? And the secant, now this is another function that I would not expect you to know what the graph looks like. But the secant, if you graph the secant, it looks sort of like this. It has these same asymptotes, but then it also, there's like one, there's sort of one down here and then another one up here. This is the graph of secant. Very strange, but anyway, when x is approaching pi over 2, again, this one gives you something which is like infinity, all right? So this also is going to be infinite because near pi over 2 to the left, the value of the secant is going to infinity, all right? So anyway, you do get infinity minus infinity. This is indeterminate form. Infinity minus infinity, all right? And so we must make a fraction. That's how we're going to handle this thing, all right? Now, in the previous example, we sort of turned a multiplication into a division by the reciprocal. That same idea is not really going to work in this case because I don't even see anything that looks like multiplication here that I can turn into a fraction. Anybody have another idea? Actually, there's sort of a different approach that would turn this into a fraction. Yeah?
Turn and like cos over sine or something.
Yeah, right. Cos over sine or something like that. Something like that, meaning sine over cosine is what tan is. And then secant, anybody remember what secant is? I hope you all remember, yeah? Yeah, secant is 1 over cosine. So that's how I'm going to, you have to make this into a fraction in some way. And just depending on the different problem, it's going to be a different, you're going to have to use different strategies depending on what you see. But anyway, this I'm going to write, my goal is to make these both into fractions. I'm going to say sine x over cosine x, and then minus secant is 1 over cosine x. All right? Really what I want is one single fraction. This is two fractions subtracted, but they have the same denominator, and so we can just subtract them. Like they have a common denominator already, and so this is the same as x goes to pi over 2 from the left, sine x minus 1 divided by cosine x. And now I'm feeling good about this. It's just a single fraction. And what happens if we try to plug in here? Actually, now when we try to plug this in, we don't even get like infinities or anything. I'm going to get sine pi over 2 minus 1 divided by cosine pi over 2, no minus 1 on the bottom, right? And what is that? Any trig masters? I've noticed, by the way, on the quizzes, folks' trigonometry has been improving. So you have been studying. That's great. What's the sine of pi over 2? I see some fingers. Yes, it's 1. The good finger. Don't show me the bad finger. This is a 1 minus 1. And the cosine of pi over 2, you can show me the fingers on that. That's 0. So this is 1 minus 1 over 0. That is 0 over 0. And I'm feeling good about this because this means we can just do the ordinary L'Hopital's rule. And I don't have to be nervous about infinities. Infinities kind of make me nervous, but 0 over 0 is much more my speed, all right? So I'm going to do the L'Hopital rule back here. We do the derivative on the top and on the bottom. And the derivative on top, sine x becomes cosine x, and the minus 1 goes away. On the bottom, cosine, the derivative of cosine is negative sine x, like that. All right? That's my L'Hopital rule step. Now we're going to try to plug the value in again, and I think actually we will get some kind of answer this time. It will now say cosine pi over 2 divided by negative sine pi over 2. And these are those same values that you just said. Cosine of pi over 2 is 0. Sine of pi over 2 is 1. So this says 0 over negative 1. And what's your interpretation of that? That's just 0. Yeah, you may feel like, does this mean like does not exist? Or no, this is 0 divided by anything is just 0. If you had 0 in the denominator, you'd say the limit does not exist. But this, no problem. It is 0. All right? I hope you don't mind. I just did two complicated examples. Both of them, the answer was 0. Of course, it's not always going to be 0. All right. Any feelings about those? All right. I got some for you to try. See how you feel. Yeah. See how you feel. The first one is the easy one. I mean, easier than all this other stuff. All right, see what you think. After this, we'll do something completely different.
And I just did roll call, yeah.
So when you get anytime zero, that or you could do there's two ways to do it. How's it going here? Can I make a suggestion? This is not wrong, but there's actually an easier way to make that into a fraction.
Yeah, that's what I did. I did the derivative twice.
Six times infinity.
Yeah, that's what I did 6 times infinity. To infinity. No, I took the second derivative. No more x's, no more infinity, but that works.
Okay.
I need help with where am I supposed to go?
Yeah, so because you get infinity over infinity, that means you should be able to tell rule again. This right here is not wrong. It was a better way to study this. You decided to keep the E on top and send this to the bottom. Where's it going here? Yeah, this e to the minus x. I started playing it. Still terrible. Yeah, same thing. X squared. You should write this all as x to the minus x. Yeah, just x to the minus x. And then do this. You can break the game. Okay. I would say you are going to go ahead and say, yeah, because these powers are best. Can we discuss these? I see some people making some good progress. These are kind of tricky. The first one is not so hard because you can basically just do the L'Hopital rule directly. So here, when I try to plug in, I will get infinity over infinity. That's because up top, 3x squared, if x becomes infinite, that's going to be infinite. And on the bottom, that other thing, again, if x becomes infinite, that's going to be infinite. So you get infinity over infinity, which means I can do the L'Hopital rule. I will get 6x on top and 2x plus 5 on the bottom. And again, this looks like infinite over infinite because if I let x go to infinity up top, that's going to be infinite, and same on the bottom. So I can do the L'Hopital again. I get, well, inside the limb, I suppose, 6 over 2. And the answer is 3. And pretty much everybody works that one out. Excellent job, pretty much everybody. The next one. This, people realize, when you plug in here, the x going to infinity, this looks like of course, e to the minus x is the same as 1 over e to the x, right? So this is really x times 1 over e to the x. That's what e to the negative x means. And if I make x go to infinity here, this becomes like infinity first and then 1 over infinity, which of course is 0. This is like infinity times 0, all right? And that is an indeterminate form, which means we need to use the L'Hopital's rule on that. When you see 1 over infinity, that you should consider to be 0. So you have to, this is one of those infinity times 0 situations. You have to go back and write the thing as a fraction. And actually right here, it's almost a fraction. There are two ways to write this as a fraction, but I think the most sensible way would just to combine these and say x over e to the x. That's the best way to write this as a fraction. X over e to the x, right? Some people, as I was going around, wrote e to the minus x over 1 over x, which is not wrong, but much harder to deal with. This is a lot easier to handle, x over e to the x. And this, when I plug in, like when I make x go to infinity, this looks like infinity over infinity, so I can do the L'Hopital rule here, and I will get derivative of x is 1, derivative of e to the x is e to the x. And now when you plug in here, you get 1 over infinity, which is 0, and that's the answer for this one. Right. Any questions about this? I saw people were more or less coming around on this one as I was going around. A little tricky to rearrange the fractions in the proper way. All right, and then the final one. X squared sine of 1 over x. This is the hardest of them, in my opinion. Again, you could start by trying to sort of plug the infinity. We get x squared, which is going to become infinite. And then I have here something like sine of 1 over infinity. Sine 1 over infinity, of course, you consider to be 0. And sine of 0, so this is like infinity times sine of 0, right? And sine of 0 is 0. So this is like infinity times 0, which means this is a indeterminate form that I should use L'Hopital's rule on. And so we're going to go back to the beginning and force this to look like a fraction. Again, there are two ways to do that. In this example, I think the easiest way would be to send the x squared into a denominator with the negative exponent. So here, I am going to change this into sine 1 over x divided by x to the negative 2. I guess the alternative would be x squared on top and 1 over sine 1 over x on the bottom, but that's a lot more complicated. This is the better way to make that into a fraction. All right. Now I'm going to do my derivatives on the top and the bottom. I guess to me the bottom is a little easier. I get negative 2x to the minus 3. That's just the ordinary power rule. Can anybody say what's the derivative on the top? I know some of you worked this one out. Yeah?
1 over x times negative x to the negative second.
Excellent, yeah. This is a young man who knows the chain rule. Remember the chain rule, when I have something on the inside of something else, you take the derivative of the outer thing, which makes a sine becomes a cosine, and then same thing on the inside, separately, times the derivative of the inside, and that's this. All right? This is a little complicated at this point, but we can simplify the x's, right? I have a power of x up here and a power of x down here. When we cancel them out or rearrange them, really I would consider negative exponent in the bottom is the same as that positive exponent up the top, and similarly with the other one. This I would write as, just to simplify matters, cosine 1 over x. This x to the minus 3 on the bottom is really the same as x cubed on top. And x to the minus 2 on top is the same as x squared on the bottom. And there's this 2 on the bottom. We also have a minus sign up top and a minus sign on the bottom, but those can cancel out. All right? I am just rearranging the negative exponents. Everybody, upstairs goes downstairs. All right, and then x cubed and x squared can cancel, leaving just x on top. So my finally simplified version of this is cosine 1 over x times x over 2. All right? We have an x up top. And now I'm going to try to plug this in again, and hopefully we will not get infinity times 0 again. We get, when we plug in, cosine 1 over infinity times infinity over 2. This over 2 isn't really going to matter, I don't think. What do you make of cosine 1 over infinity? This is the same as cosine 0, because 1 over infinity is the same as 0. So this is cosine 0. And what is cosine of 0? I see the finger. 1. So this is 1. 1 times infinity over 2. What's your interpretation of that? I would say this means infinity, all right? If the infinity is on the bottom, that might mean 0, but this is sort of like infinity times a half. This is, infinity is the answer. So you could say the limit does not exist, or you could say the limit is infinity. All right? Any thoughts about that one? This is kind of the hardest one that we're going to do. These, of course, if you have a calculator, you can check your answer by graphing this function. You should see, if you look at the graph of this, not that, the original thing, as you go out to the right, you should see the graph goes up forever to infinity. That's why this limit is infinity. All right, that's a hard one, the L'Hopital's rule. All right, excellent. I think that's all we need to say about L'Hopital's rule. So this will be on the homework for next week, not this week. All right, excellent. I think I'm ready to move on to the next topic. So I believe on the big list, this was number 10, L'Hopital's rule. The next one is, actually, we're moving into a new chapter in the book. Chapter 7 in the book is about integration techniques. That is like different tricks for doing different kinds of integrals. So far as tricks for doing integrals goes, really we've got the u substitution and that's it. This is the only trick that we have discussed for doing integrals. But we are, over the next few times going to talk about a few more integration techniques. And the first of these is called integration by parts. So this is a trick for doing certain integrals. Where the u substitution doesn't work. All right. If you just show me a weird integral, there are a few different tricks that I know to try. I'm going to start by trying the u substitution, because that's the standard trick that hopefully is going to work. But if that doesn't work, you might have to try integration by parts, or maybe one of the other ones that we're going to talk about over the next few weeks. But integration by parts is, I would say, maybe the easiest of these ones that we are going to discuss. And this is a trick which is based on the product rule. The u substitution is more or less based on the chain rule. The u substitution technique is sort of like an integral version of the chain rule. The integration by parts is inspired by the product rule. And I want to show you where it comes from, because it's actually very simple where it comes from. If we write the product rule, writing the product rule in the usual way, I don't usually write the formula out like this. But if you wanted to write the formula out, it says the first thing times the derivative of the second thing, it's f of x times g prime of x plus g of x times f prime of x, right? This is the product rule, which I'm sure you wrote down in your notes at some point in your Calc 1 class. The first thing times the derivative of the second thing plus the second thing times the derivative of the first things. I'm going to write this in kind of a much simpler way, but this is a more familiar or a more friendly way if you're talking about integrals to write it in this way. The derivative of u times v, it shall be the u times the derivative of v plus the v times the derivative of u. All right. I'm writing it in just a different way of writing things, using d for derivative, all right? But this right here, we can just take the integral on both sides of this formula. So I'm going to do integral on both sides. It says integral duv equals integral u dv plus integral v du. All right. I sort of broke up the integral on the right-hand side into two separate things. That's because if you have things added together inside the integral, you can break it up into the two integrals added together. And then one last thing is, on the left side, what you see is integral of the derivative of uv. But the integral and the derivative are inverses to one another, like it's the antiderivative of the derivative. Those should cancel out, and I just get uv on the left side. Come on now. So the left side is just uv equals integral u dv plus integral v du. And this is basically the integration by parts formula, although usually we write it the other way. So I'm going to rearrange just by subtract this integral v du onto the other side. And then I'm going to write it the other way around. uv minus integral v du. All right, this right here is what we call the integration by parts formula. And you need to memorize this. And we're going to do it so often that I don't think you'll have a problem memorizing this. But this is the integration by parts formula. All right, integral u dv equals uv minus integral v du. You can do this, or you can use this in order to do integrals of things where the u substitution doesn't work. And the process of doing this involves we must sort of look at our integral and choose which part is the u and which part is the dv. All right. So in this way, it like the sort of like the vibe when you're doing this is kind of similar to the u substitution, in that in a u substitution you have to look at this weird thing and choose a piece of it to be the u. The integration by parts is similar, only you're going to have to look at something and you choose one piece to be the u and you choose another piece to be the dv, and then you do this integration by parts formula to it. All right, let's just try a simple one, and then we'll of course have sort of a few examples of increasing complexity. This is like everybody's first integration by parts problem. X times e to the x. Absolute classic integration by parts problem. X times e to the x. All right. When you see something like this, it's not a bad idea to consider, maybe I can do this using a u substitution. But actually the u doesn't really help. You would have to choose either, maybe you would choose u to be the x, just because that's inside of the exponent. But then you have nothing to do with this x over here. The u substitution just isn't going to work. Instead, I'm going to do parts, and I will choose, now just like the u substitution, you have to do a bunch of examples to get a feel for what do you usually want to pick for the u. There are similar guidelines for parts, but just for now, I'll just tell you what to choose. I'm going to choose u to be x and dv to be e to the x. All right. You have to look at these two parts, and I'm here to tell you, dx you always include as part of the dv. So these two parts, I chose that to be the u and that to be the dv. All right. How did I know to choose it in this way? Just because I know, but we're gonna talk about that after a little bit. There are some basic guidelines about how you should choose one or the other part. All right. Now I intend to use the formula in the box up there. Integral u dv equals uv minus integral v du. Now, in order to use the thing on the right-hand side, like what I chose here, I do actually have integral u dv, right? Now, I'm going to use this stuff. This stuff involves v, and also du. And we have to just work those out, but this is not hard to do. I choose those, and then we find du. Well, just like in a u substitution, du is the derivative of u. U is x, so du is just 1 dx. This is how, exactly like how we do it in a u substitution. The du is the derivative of u. What about v? This is a little, I mean, we don't do this in a u substitution, but it's not so hard. I know what dv is. To find v, you do the integral of dv. It's the antiderivative of dv. So this v, I figure by doing the integral of the dv, right? That would be integral of e to the x dx, and that is just e to the x. All right. So now we know all our u's and v's and du's and dv's, which means we can just plug everything into the formula. So I'm going to go, my integration by parts formula, this here equals uv minus integral v du. That's the formula in the box. And we should be able to plug everything in that we've worked out here. So u is x, v is e to the x, it's right here. V is e to the x minus integral v is e to the x, du is 1 dx. Would you mind if I just say dx? Like that. All right. This is what we get after plugging into the integration by parts formula. Now, we're not entirely done here because I still see an integral here. So we're not done because we still have a new integral to do. But the point of all this is like this, at this point, this is an easy integral to do, right? We started with a complicated one and we did some steps and ended up with an easier integral to do. But anyway, the final step here would be to actually do that second integral. I leave e to the x, or x e to the x like it is in the front, minus integral of e to the x is e to the x. And now now we're really done. I put the plus c, and that's it. All right. Integral of x e to the x is what we started with. The answer is x e to the x minus e to the x. This is the integration by parts. Anybody got a question about it? Yeah?
Is there any reason why when you do the derivative of v, it's not e to the x plus c, or can you just like ignore that one?
Yeah, put the plus c here. This is a good question. The answer is we are never going to put the plus c here. But you could if you want. Like if you decide to put the plus c here, really the effect of that would be to insert the plus c here, and then at the end you'd have sort of like two different plus c's, which you might as well just write as one plus c. So the answer is, on some technical level, you kind of should put the plus c here, but it ends up never mattering, and you might as well just put the single plus c at the end. Yeah, this is a good thing to consider though. All right. Excellent. That was a simple example. Let me talk about like general principles here. Generally, this is about to choose the u versus the v. How did I know in that particular example I wanted to choose the u to be x, and I chose the v to be the other, or the dv to be the other thing? The general idea is, notice that when we use the formula in the box, what we started with is u inside the integral, and we kind of trade that for a du inside of the integral. So the idea is you want to choose the u to be something which gets simpler when you switch it with du. So we started with u inside the integral. On the right side of the formula, we have du inside of the integral. So the general idea here is to choose the u and the v. I want to pick u as something which simplifies when we take the derivative, because you start with u inside the integral, and when you use the formula, it changes into a du, all right? And I want the du to be simpler than the u. And that's why I picked x, because using u equals x makes du equal just 1, so the thing just goes away entirely. Pick u as something which simplifies when we take the derivative. So in this case, I would like So I would say good choices for you would be power of x. If you ever see just a power of x, this was x to the 1. That's the classic choice for u. You should choose that part to be u. Power of x, can I say, or polynomial, right? This is similar. A power of x or a polynomial will always get simpler when you take the derivative. The degree will decrease, all right? So this is a good choice for you. Another good choice for you is ln of x. It didn't come up in that example, but if you see ln of x, that's kind of a weird function by itself, but when you take the derivative, it becomes 1 over x, which is a lot easier to handle, all right? So these are good choices for the u. They are generally bad choices for the dv, that's the other part. But these are good choices for the u. And I will say, just as a third one, can I say sometimes e to the x. I say sometimes because e to the x actually doesn't get simpler when you take its derivative, but at least it doesn't get more complicated. So e to the x sometimes will work, although usually we don't want to make that the u, okay? And then good choices for the dv is basically the opposite. So powers of x and ln of x are bad choices for the dv. I will say good choices for the dv is typically exponentials. Usually you don't want to use polynomials or ln. You essentially never want to use ln of x for the dv, all right? Good choices for the dv would be something like e to the x, like the one we just did. Then it doesn't get simpler when you take the antiderivative, but at least it doesn't get any more complicated, all right? So this is generally a good choice for the dv. And I will also say, just like in the u substitution, sometimes you need to break the rules. These are not hard and fast rules here. And as you know, there are examples in a u substitution where, for some reason, choosing the u in a weird way is actually helpful. And the same is true for integration by parts. Sometimes there are weird examples where you just have to choose something weird in it and it will work out. All right. But these are the general guidelines, which I have written up there. All right. I got 2 more examples, and then I have some for you all to try. And maybe I got 2 more, and then I got 1 for you. And I think that'll do it for our time together. Let's try this here. E to the 4x times 3x minus 2 times dx, all right? I'm going to do the parts, and we have to begin by choosing which part is which. The parts are always multiplied together, right? And so really it's going to be those 2 things. E to the 4x should be one of them, and 3x minus 2. Anybody, based on my general principles here, what do you want to pick for the u? I think I heard somebody say 3x minus 2. That's the polynomial part. I like that. What I said up here, pick the u as something which simplifies when we take the derivative. So a power of x or polynomial is always, well, not always, because I said sometimes there's weird examples, but power of x or polynomial is a good choice for the u. So that's what I'm going to choose as the u, which means the other part is going to be the dv. So u is 3x minus 2. dv is e to the 4x dx. Can I just say, as a technicality, dv always includes dx, and du always includes dx. This is just how it always works out. I hope, by the way, your handwriting will allow you to tell the difference between a u and a v. So I always put a little tail on my u so that it doesn't look like a v. This v looked kind of like a u, but it don't got the tail, so I can tell it's a v. Okay, anyway, what's the du? The du is the derivative of that. What do you say? I see 3 on the fingers. 3 dx. That's the du is the derivative of the u. And the v is the integral. So this v is integral e to the 4x dx. Anybody remember what that is? We actually talked about a useful little formula for integral of e to the x, but when there's a constant up top. This is something that I said was going to be worth memorizing. It hasn't come up since I said that, but actually we're going to deal with it very often. The integral of e to the kx is 1 over k e to the kx. This is a cute fact which comes up often enough that it's worth just remembering this. If you have an extra constant upstairs in a e to the x, the effect is you just have to divide by that constant. So this integral of e to the 4x is 1/4 e to the 4x. And as we discussed before, I'm not going to put the plus c just because in an integration by parts you don't need to. All right. All right, let's put it all together then. So I go uv minus integral v du. That's the integration by parts formula. And we just got to plug everything in. So u is 3x minus 2. And then the v is 1/4 e to the 4x. Haters, put those parentheses in there. It matters. It should be all that 3x minus 2 times the e part. All right, and then I go, that was uv, and then I go minus integral v. V is 1/4 e to the 4x times du is 3 dx, like so. All right. Okay, so this stuff out here is just going to stay like it is forever in the answer. Now we have to do this integral. This is not so hard to do, although I would like to simplify a little bit before I try to do this integral. We have constants multiplied on the inside. They can just pull out of the integral, and this is very common. You usually, before trying to do that last integral, you usually want to simplify it a little bit. I'm going to pull the 3 out and also pull the 1/4 out. It comes out as a 3/4 integral e to the 4x dx, right? And now, can we do integral e to the 4x? Actually, yeah, it's actually the same as the v, which you can still see up there. When I do integral e to the 4x, it becomes another 1/4 e to the 4x. So this will be my final answer. 3x minus 2, 1/4 e to the 4x minus 3/4 times 1/4 e to the 4x. Right? This 3/4 stays like it is. This integral e to the 4x becomes 1/4 e to the 4x. All right. That's what I think. Any questions about that one? All right, I got one for you to try. And maybe that'll do us for today. How about integral of 3x squared over e to the 5x? Now this one has a little bit of a little technicality to begin with. This is a fraction. The integration by parts formula does not work for fractions. It only works for multiplications. So we can just do the very first step together. If you intend to use the parts formula, you must write it as a product, not as a fraction. So your very first step here should be, can anybody suggest how can I write this instead as a product? Sorry, it's now occurring to me. I didn't mean to put x. Can I just put x up there, not x squared? It's not impossible with the x squared, but that's, I want to talk about that before we actually try and do it. Can anyone suggest how can I write this as a product, not a fraction? Yeah? Yeah, she said make the what is in the bottom, write it using a negative exponent instead. So it's going to be 3x times e to the negative 5x. That's a product. She wrote it the other way around. It doesn't matter. You can write it however you like. All right. Anyway, try the parts on that. See how it goes. You cannot do the parts on a fraction. It has to be written as a multiplication. Folks are doing fine. Nobody wanted to talk to me because everybody was just diligently working it out. And I think everything looked good. The u, you want to choose 3x for the u, and the dv, e to the minus 5x. So the du then is 3 dx. The v is 1 over minus 5 e to the minus 5x. Make sure you keep that minus sign there. The minus sign is part of the constant up inside the exponent there, so it's like that. And then I think I'm ready to do my my integration by parts formula. I go uv minus integral v du. Hopefully you are beginning to memorize that. That's the u. The v is 1 over minus 5 e to the minus 5x, and then I go minus integral v 1 over minus 5 e to the minus 5x. Du is 3 dx. All right. Next, I would simplify inside the integral. You can pull the 3 out and also pull the negative 5 out, negative 1/5, and you're going to end up with a plus on the outside. Can I gather these constants together? 3/5 x e to the minus 5x, and then this time it'll be plus 3/5 integral e to the minus 5x dx. Right? I pulled the 3 out and the 1/5 out. I had 2 minus signs, so I made this a plus right here. And then finally, the integral of this becomes another negative 1/5. So I get minus 3/5 x e to the minus 5x plus 3/5 times 1 over minus 5 e to the minus 5x plus c. There you go. This is how we do it. This is the integration by parts. So these two have been, I would say, easy ones. Next time we'll do some more complicated ones, some little variations. Although really, in my opinion, it doesn't get very complicated. The integration by parts to me is not so tricky. All right, I think that'll do for today.